All right, welcome back. So now that we've looked at different things that we can do within Simulink and we looked at a simple example, let's actually do some practical applications of Simulink. So what I want to do for this first project is I want to simulate a bouncing ball. So we're going to see how we can simulate a bouncing ball using Simulink to determine both its position and its velocity throughout the simulation. So this is going to be a very practical example and something that we can actually picture in real life. And we're going to see how we can simulate that behavior using Simulink. So first, before we move into Simulink, let's actually define the project and let's define the problem that we're trying to simulate. So what I'm going to do here is I'm going to draw basically what we're trying to do with this project. So again, what we're trying to do is basically simulate a bouncing ball. So imagine that you have the ground over here. So I'm going to draw here, this is the ground or the floors. So this right here is ground. And we're going to hold a ball at a certain height above that ground. So let's say that the ball is somewhere around here. Again, this right here is the ball. So what we want to do with Simulink is we want to see, well, let's say that we drop that ball and that ball is at a certain height, X above the ground, or actually let's call it Y. So the height or the distance from here, so in other words, from the position of the ball to the ground, we're going to call Y. So Y is going to be the position, essentially the height at which the ball is above the ground. So let's say that then again we have a ball that we're holding at a certain height above the ground, and then we drop that ball. What we want to do is we want to simulate, okay, how does that ball drop and then bounce from the ground and then keep bouncing. So we would expect something like this, right? When you drop a ball that's somewhat elastic, it bounces back, but when it bounces back, it doesn't quite reach the same height that you dropped it from. Then it keeps going down, bounces again, it comes back up, but it doesn't come up all the way to the initial height or to the previous height. And that keeps repeating until eventually the ball is at the ground. So it's at a standstill at the ground. So that's what we're trying to simulate. We're trying to simulate that behavior. And again, we're using this as an example so that you can see that Simulink can be used to model different physical phenomena. Something as simple as just dropping a ball above the ground. We can use Simulink to simulate the behavior of that. So this is a very practical example. Now there's a couple of things that we need to define first before we can actually simulate that using Simulink. And that is, again, we're going to define two things. The position of the ball above the ground, that we've called Y over here. And then we're also going to define the velocity of the ball. So of course, if you drop a ball above the ground, you're starting from zero. Let's say you don't apply an initial force up or down. You just simply drop it from a certain height. That ball is going to accelerate down due to gravity. So it's going to start at a velocity of 0 meters per second, and then it's going to accelerate as it goes down because, again, the gravity is pulling it down and it's making the ball accelerate. So the velocity is going to increase as it goes down. So there's going to be two equations that we're going to define for this problem. One is the rate of change of the velocity with respect to time. So again, we have two variables over here. We're going to have v of t, which is going to be the velocity, and we're going to have y of t, which is going to be the position, essentially the height at which the ball is above the ground. Now we know from basic physics that the position is, or rather the rate of change of the position is equal to the velocity, and the rate of change of the velocity is equal to the acceleration, which in this case would be gravity. So in other words, we can write the equations for both the velocity and the position as follows. So we're going to have dv So the rate of change of the velocity with respect to time, so dv dt, the derivative of the velocity with respect to time, is going to be equal to minus g, which again would be the acceleration. In this case would be g, which is gravity, and then minus because it's pulling it down instead of up. So that's going to be our equation number one. And then we also need an expression for the position as well. And again, from basic physics, we know that the rate of change of the position is going to be equal to the velocity. So in other words, written down in equation form, dy dt, so the rate of change of the position with respect to time is going to be equal to v, where v is the velocity. So these are our two equations that basically define the behavior of this bouncing ball. So what we need to do then is we need to find an expression for both the velocity and the position, but not the rate of change as we have over here in equations 1 and 2. So essentially what we need to do is we need to integrate those equations. So if we integrate both sides of the equations, we would get the following. So v of t is going to be equal to the integral of g of t, or rather minus g of t dt. And then same thing for the position y of t. So the position as a function of time is going to be equal to the integral of the velocity vt, or rather v of t dt. So what we need to do then in Simulink is we need to find a way that we can represent these two equations using Simulink blocks. And then we're also going to have to give it, of course, the initial position of the ball. So that we're going to call y of 0, essentially this position again. The initial position of the ball, y of 0 is going to be initial position. So that could be 10 meters or 20 meters or 100 meters, wherever you're dropping the ball from. And then same thing for the velocity. So v0 is going to be the initial velocity. So in other words, if you're simply dropping the ball, you're not applying any force initially, then v of 0 will be, of course, 0 meters per second. Now you may not only be dropping the ball, but you may be throwing it up and then it comes back down. So in other words, you might be doing something like this, to where you initially apply some force up, so the ball moves like this. In that case, of course, the initial velocity would be something positive. So it could be something like positive 5 meters per second. Or you could also be doing the same thing down. You might be applying a force down to where you kind of push the ball down. In that case, the initial velocity would be something like minus 5 meters per second or something like that. And again, if you're simply just dropping it without applying any force, then the initial velocity would be just 0 meters per second. All right, so now that we've defined our problem and we have some equations that we need to simulate using Simulink, let's move into Simulink and let's see how we can basically represent these equations using Simulink. All right, so we're gonna build this entire model from scratch using just simple blocks from Simulink. And again, what we're trying to do is we're trying to simulate that bouncing ball where we derived the two equations for. So we're gonna need a few blocks, but the main one is gonna be what's called an integrator, which of course we're gonna use, again, if we go back here to the equations, we're gonna use to represent these two equations over here. So we need to integrate essentially the gravity and the velocity. So we need to find in Simulink again what's called an integrator block. So again, you're going to find blocks in the library browser within Simulink. So let's go ahead and click on that, and you can do a search for what's called an integrator. And again, this is just basically what the name implies, is an integrator. It integrates, or it's basically the integral of whatever you're feeding into that block. And again, just like anything, you can do right click and go to help for the integrator block. And then you can see the documentation there for the integrator block. But as the name implies, basically what it is you feed an input, and then this block makes an integration of that input and then presents that to the output. So if you feed it the velocity, then you essentially are integrating that, and then the output of that would be the position, which is what we want. So let's go ahead and add that to the model. So let's click on that, and we're gonna need a few other blocks. Let me actually, I think I just opened the help menu. Let me add it to the model, and we're gonna need 2 of those, but we can just make a copy of that in the model. So we're gonna also need, again, I mentioned that here in the equations, we're gonna have some initial conditions for both the position and the velocity. So we're gonna need what's called, again, an initial condition block. So if I go over here to the library browser, I can do a search for initial condition and just click search, and that's gonna give me this block over here, which is an initial condition block. So let me add that to the model, and I'm gonna add a few more things, and I'm gonna explain in the model what they're used for. But I'm gonna need a go-to and a from block. We used those before to kind of organize our model a little bit better. So let's go ahead and add those. Here's the from block. Let's add a go-to block as well. I'm gonna need constants, so I can search for a constant. And again, I'm just searching for these now, but I'm gonna explain that here in a second in the model. So I'm gonna need a go-to block, from block, a constant, a scope. Again, scope is what we use to kind of see our simulation or see the behavior of the simulation. I'm also going to need a gain block. So here's my gain block. And I'm going to need a what's called a relational operator. I think that's the name. It's basically if you're trying to do a greater than or less than or equal to, that's what you would use this block for. So let's go ahead and add that, and I think that's everything we're gonna need. So now let's go back into the model, and again in here I have my relational operator, the gain, the scope. Let me move that scope here to the right. I have my constant over here, a go-to block, and a from block, and the integrator here, which is the main component here in our simulation. So let me make this one a little bit bigger. All right, so again, essentially the integrator, what it does is, again, as the name implies, it integrates the input and presents that integration to the output. So for example, over here, if we're trying to get the velocity, we need to integrate the gravity or the negative of the gravity, that is. So basically this equation over here. So let's go ahead and basically mimic this equation in Simulink. So again, to get the velocity, we need to integrate the gravity, but we know that gravity is constant, right? Gravity is just simply 9.8 meters per second squared, and that doesn't change with time. That's just a constant. So in Simulink, then what we can do, going back here to Simulink, I can say, well, I'm going to take a constant, and this constant is going to be, if you double click on that, the value of that is going to be minus 9.8, which again is the gravity. So this right here, let me actually change the name over here. This is gravity, which again, gravity is equal to 9.8 meters per second squared. So what we're saying here is that if we feed that gravity into this integrator, the output of that is going to be the velocity. So let me go ahead and put that over here. I'm going to say then that this right here essentially is going to be the velocity, and I'm going to call that simply just v. And let me actually rename this. This is the velocity. And let's match this from tag. So again, all I'm doing here is I'm feeding that output into this go-to block. I'm calling that the velocity, and I'm doing that such that then I can use from blocks to get the velocity. So if you go here and click update tags, And now let's go here to the drop down. We'll see the velocity over here. All right, so essentially, again, I mentioned this before in a previous lecture, but essentially there's a virtual connection between this block and this block. And we're doing this just to keep things a little bit more organized. So this right here is essentially doing this equation. Again, the velocity is the integral of the negative gravity. And again, if we go back here to our model, that's essentially what we're doing here. We're taking the gravity, negative gravity, that is, because again, gravity is pulling the ball down, and we're integrating that, and the output of that is the velocity. So that's what we're doing here. Now we also need to define an initial condition, because again, we're going to have an initial velocity and an initial position for our simulation. So essentially, we need to define an initial position, or rather an initial condition, and feed that into this integrator block. Now if you double click on this block, you'll see over here that you have several options, one of which is the initial condition and the initial condition source. So you can either just give it some value over here, or you can give it an external initial condition source and then feed that initial condition into the block. And that's what I'm going to do for this example. So I'm going to say, notice here that there's no more inputs in the integrator block over here. But now if I say initial condition source external and I click apply, notice that another port comes available over here, which is the initial condition. So now let me move this up a little bit and let's move this down. So now I need to feed my initial condition here to this point over here. And again, that's why we're using this block over here, which is simply an initial condition. Now, for this example, or just to start, let's say that we're not applying a force prior to dropping the ball. So essentially, the initial velocity is 0 meters per second. So again, we're simply just dropping the ball. We're not throwing it up or throwing it down. We're just simply dropping it. So the initial velocity is going to be 0. Of course, it's going to accelerate down because gravity is applying a force to the ball, which is pulling the ball down. Right, so the initial condition, again, is going to be 0. Now, the nice thing about this initial condition block is that it gives the block an initial condition, but it only holds that initial condition for the first time, or rather, from the initial operation. But then you can also feed a previous execution here to the input of the block. So in other words, I can say that I'm going to feed this back over here. And what that would do is I would take this input, integrate it, and then the output of that integration is going to come back. And now that's going to be my initial condition for the next calculation. So originally, in the very first calculation, this block, the integrator block, is going to take the initial condition to whatever we tell it to using this block. But then after that, it's going to feed whatever we're feeding into its input. So that's helpful because this block is essentially doing integration one time, then do it again, then do it again, then do it again. And we don't want to keep feeding this initial condition because we know that the velocity of the ball is going to keep decreasing every time it bounces. So instead of telling it to always take 0 meters per second, we can tell it, use that initially, run the first iteration, so the first bounce of the ball, and then after that, use whatever you had as a result for the previous iteration. So that's the nice thing about this initial condition block. So again, we're telling it essentially we're going to drop the ball, so the initial velocity is this number over here, is 0 meters per second, but then after that, take whatever you calculated the previous iteration. Now the reason why we need that is because we know that the ball is going to lose energy every time it bounces. That's the reason why when you drop a ball and it bounces, it never bounces back to the original position. It bounces back a little bit lower than the initial time or at the previous time. Then it bounces again. It bounces up but lower than the previous time. And it keeps repeating that until it essentially settles down in the floor or in the ground. So that's why we need this initial condition block. And now we're also going to have to define this constant over here. This is going to be the restitution constant. Restitution. Let me actually rotate this. I'm going to click Control R, and I'm going to explain here in a second what this exactly is. But let's change the value to minus 0.7. And this could be minus 0.7, minus 0.8. It depends on how elastic the ball is. But again, I'm going to explain this here in a second, but let's feed the velocity back and let's feed this to the initial condition. All right, so what basically this block is doing is it's saying, well, you have an initial velocity, but then when the ball bounces back, it loses energy when it bounces back. So you need to have a way to represent that loss of energy, and that's what this constant is doing. So basically what this is saying is, you're going to have an initial velocity, you're going to drop the ball, it's going to bounce back, but then after that, the velocity is not going to be whatever it was before, it's going to be whatever it was before minus 30%. So it's going to lose 30% every time it bounces back. So that's what this minus 0.7 is. 0.7, of course, being 70%. And that's just an assumption based on the ball. Again, more elastic balls are going to have a number closer to 1. So essentially they could bounce back almost close to the initial position. And if you have something that's not very elastic, let's say like a baseball, something that's more rigid that doesn't bounce as well, then that number would be closer to 0. So maybe it's something like 0.1. Essentially what this represents is whatever energy is lost during every bounce. And again, the more elastic, the closer that number is going to be to 1. The less elastic, the closer that number is going to be to 0. So I'm just using 0.7. Let's say that that's, for example, for a tennis ball or something that bounces fairly well. All right, so now we have this. We've defined the velocity, or rather we've calculated the velocity based on the integration of the gravity. Again, that's this equation over here. We've also given it the initial velocity. We've made our feedback loop over here so that we represent the loss of energy during every time the ball bounces. But one more thing that we need to do is we need to reset the calculation every time the ball reaches 0. And actually just noticed a mistake over here. This shouldn't be coming back from the velocity. This is coming back from the state port. So you can double click on this block and click show state port. That's gonna come up over here. And essentially what that is it gives you the value of the calculation at every point in time. So it's still the velocity, but it's the calculation at every point in time. So this restitution again is a representation of the loss in velocity every time. So we gotta find, or rather we gotta show the state port, which gives us the state of whatever variable we're integrating, and then feed that to the restitution block. Now one more thing that I wanted to show here is again that we need to recalculate the velocity every time the ball reaches 0. So every time it bounces, when it hits the floor, we need to recalculate everything. So to do that, what we can do is we can say we're going to have an external reset, and we're going to reset it when it's a rising edge. And let me move this up, and I'm going to explain here in a second what exactly that means. So essentially, this integrator block can be reset every time something happens. So we've defined that we want to have an external reset, meaning we're going to redo the calculations, redo the initial conditions, redo everything every time this port over here is a logical one. So the reason why we want to do that is because we want to recalculate everything every time the ball reaches the floor and it bounces back. We want to reset the initial conditions and reset the calculation. So we're going to have a reset condition there. And let me use this from block. I'm going to make a copy. And let's put that over here. And I'm going to rename this. This is going to be reset. And I'm going to call that RST for reset. Now we haven't defined it yet, so this might give us an error, but we've essentially done the velocity integrator over here. Now we need to do the other equation, which is the position. So this equation over here. Now notice that this one is that the position is the integral of the velocity. So that's why we had to do the other one first. So now we have the velocity over here. And again, we've defined this go to and from tag. So these two variables are essentially the same. So now we can say, well, now we have to integrate the velocity to get the position. So instead of integrating gravity, now we're gonna integrate the velocity. And again, all that's doing is it's representing this equation over here. The position is the integral of the velocity. All right, so again, we're doing the same thing here. The integrator, this one over here, is going to be what we're going to use to get the position. To get the position, we have to integrate the velocity. So we're feeding the velocity from here to here. Now we're going to have the same reset. So every time the ball reaches 0, we're going to reset our calculation. And we also have to have an initial condition. Now for the initial condition, let me put that over here. We're going to say that we're going to be, let's say that we start at a height of 10 meters above the ground. So again, this could be whatever. This could be 10 meters, 20 meters, 100 meters. It doesn't matter. It's just the initial position of the ball. So let me just write it over here. This is going to be initial position. This over here is going to be the initial velocity, and these are just resets, velocity, and now we're also going to have another block like this, which again, the output of this integrator now is going to be the position. So I'm going to call this X, or rather Y for position. So Y is going to be, again, the position. Now we know, again, that we want to reset all the calculations when our ball reaches the floor or the ground. So essentially, when it bounces back, we want to reset all the calculations. So that's what we're going to use this state port. Again, the state ports are basically just, it's showing you the state of whatever variable you're integrating. So we use that here for the velocity, and we fed that through the restitution constant to get the next initial condition. But now here for the position, what we're going to do is we're going to compare that, and that's why I have this block over here. We're going to say if the position is less than or equal to 0, so in other words, once it has reached the ground, so let me make a copy of this constant. So this is going to represent the ground, and that of course is going to have a value of 0. So in other words, when the height is 0 meters, which of course means ground, once you've hit the ground, then the output of this is going to be a logical one. So in other words, again, these ports, this one over here and this one over here, show the state of the variable that you're integrating. In this case is the position, and in this case it's the velocity. So when the position reaches 0, so when this state port is less than or equal to 0, that means that the ball is at ground. It means that it has reached ground, so we need to reset all of our conditions. So now I'm going to feed that, the output of that, to this 2 block, which I'm going to call, this go-to is going to be the reset, RST. And let me just say over here, reset. All right, so let's go over this again, because I realized that it may be a little bit confusing. So this block on the left is essentially this equation. We're integrating the gravity to get the velocity. So let's go back over here. We're taking gravity, we're integrating it, that's going to be the velocity. We're taking the state of the velocity and multiplying that times minus 0.7 to get the initial condition for the next iteration. What it represents is the loss of energy every time the ball bounces. Now, this block on the right is the other equation. So this equation over here, so the position is the integral of the velocity. What that means then, again, here is we're taking the velocity, we're integrating that, and that's going to give us the position y. Now, we're using this state port, which again, this gives us the state of whatever variable we're integrating, in this case, the position. So when the position is less than or equal to 0, which is the ground, then reset both of our calculations for both the velocity and the position integrators. Because again, we want to reset the calculation and reset the initial conditions. So this block then comes over here and over here to reset both integrators. Now the initial position, again, I'm assuming that's going to be at 10 meters, and I have to feed here what's called a ground, and that's located here in the library browser. If you go to commonly used blocks, this ground over here. So essentially that's something that you use when something doesn't need to be connected, but Simulink doesn't like when you leave stuff unconnected. So let's add that to the model, and going back here in the model, we're going to feed that over here to this initial position. All right, so one last thing that we need to do is we need to limit the state of this integrator. So for the velocity, we're not going to limit the output of the integrator. So the velocity could be whatever in the positive and negative directions. Now for the integrator, we know that of course the ball cannot go any lower than the ground, right? It wouldn't make sense to have a negative value for the position because the ball is not going to go through the ground and keep going on the ground. So we need to limit the output of this integrator. So if I go over here and click on limit output, you can see that we can have upper saturation limit and lower saturation limit. What I'm going to do is I'm going to change this, instead of being minus infinite, I'm going to change that to 0. What that means is that for this position integrator, the output of that can be on the positive direction. It could be whatever. So we could tell this that the position could be 1,000 meters high or 2,000 meters high or whatever, 1,000,000 meters high, it doesn't matter. However, for the lower position, we know that of course we're bouncing a ball above the ground and it's bouncing on the ground, so it cannot go any lower than the ground, of course, because it can't go through the ground, right? So we need to limit the output of this integrator to be 0, essentially representing ground. So I'm going to click OK. And I think this is everything we need. Of course, we want to show the variables in the scope. So again, you can click on the scope and you can right click on it, go to signals and ports, number of input ports, and I'm going to change that to 2 so that we have one input for the velocity and one input for the position. So that changes this over here. And again, remember what I said earlier, that when you have complex circuits or complex models, it helps to keep things organized by having this go to and from tags. Imagine that we were drawing this reset now to here and again to here, and we also had the velocity going from here to here, and now we want to show again the position and the velocity in the scope. So we would have to have wires going from here to here and from here to here, so it would start to get very cluttered very quickly. So that's the nice thing about having go to and from tags, and you can really appreciate it in models like this. Once we start getting more and more complex models, it really helps keep things organized. So what I can do here for my scope then is I can just basically take this from block and make a copy, put it over here. This is going to be my velocity. And let me make another copy of this, and I'm going to put it over here. This is going to be our position, and of course I have to change this tag. So let me change this to y, which again was our position variable. All right, so we're ready. Again, this block on the left is basically just an integration of the gravity, which gives us the velocity. This block on the right is an integration of the velocity, which gives us the position. So now we have our two variables, velocity and position, and we're feeding that into the scope so that we can see it during the simulation. All right, so for this first simulation, let's run it for 10 seconds. And let's say that the initial velocity is 0 meters per second, so we're essentially just dropping the ball. We're not throwing it up or throwing it down, we're simply just dropping it. And let's say that the initial position is 10 meters above the ground. So let's open up this scope. And again, you can run simulations from scope. And again, notice that here the scope gives us only one trace. If you want to see the two inputs on different traces, what you can do is go to View, Layout, and change this to be one on top of each other, or you can do one side by side, it doesn't matter. I like to do one on top of each other. So the top one is going to be this variable over here, the position. The bottom trace is going to be the velocity. So going back here to the scope, let me make this a little bit bigger. All right, so now we're ready to simulate. Let's go ahead and click Run over here. And again, we're running this simulation for 10 seconds. All right, so one thing that you might notice over here is that I ran into one error. It says Simulink, or rather, let's go all the way to the top. An error occurred while running the simulation, and the simulation was terminated. Caused by Simulink will stop the simulation of model untitled because the two zero crossing signals identified below cause 1,000 consecutive zero crossings events in time interval between this time and this time. Now there's a fix for that. It says you can suppress the diagnostics and continue simulation without bracketing these zero crossings by switching the zero crossing detection algorithm to adaptive and setting ignored zero crossings diagnostics. So basically what this is saying is, notice here again, top trace is the position, bottom trace is the velocity. So we start at 10 meters above the ground, it bounces, 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 and we get to a point where the bounces are so small that Simulink is getting into an error because it's saying, well, the previous bounce was maybe like 0.0001 meters above the ground. The next one is 0.00001 meters above the ground. And it's saying, well, these two values are very, very close to zero. Is the simulation correct? So it's giving you sort of a warning saying there might be something wrong over here. However, if we look at the simulation, it's clearly correct. We're starting at 10 meters per second. The ball is coming down to zero. So this would be the floor. It's bouncing back lower, and it keeps repeating. So let's go ahead and click this ignored zero crossings diagnostic to none. So we can simply just click fix, and Simulink basically is going to now ignore that warning when we run the simulation. So now it's fixed. Let's run it again, and you can see the bouncing over here. All right, so this looks like we expected, right? This x-axis is basically time. So 0 seconds, 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds. This, again, the bottom, or rather the top trace, is the position of the ball above the ground. So our initial condition was that we're starting at 10 meters above the ground. So if we go back here to the scope, we can see that the position initially is 10 meters above the ground. Now it falls, hits the ground, bounces back up. It bounces, but it doesn't bounce to the initial position. Notice that, again, this is 10 meters. This looks more like 5 meters or so. So it falls, bounces to a lower height, then bounces again to an even lower height, bounces again to an even lower height, and it keeps repeating until it eventually settles around zero. Now, you can also just kind of zoom in over here. So to zoom in on the x-axis, you can click this drop down and click this tool over here, which is Zoom X, and let's zoom over here towards the end. So let's select that and zoom over here, and then you can do this scale y-axis. So notice here the units. So 10 times 10 to the minus 15. So 0.0 and then 15 zeros, 1 or rather 9 looks like meters above the ground. So this is of course just as accurate as a simulation is going to get. It's not going to get any more accurate than that. But you can see over here again that this is behaving the way we were expecting. Now let's change a couple things here to just see how the initial conditions change our simulation. Let's say, for example, that instead of starting at 10 meters above the ground, we start at 100 meters above the ground. So we're changing the initial condition for the position, so the initial position, to 100 meters above the ground instead of being 10 meters above the ground. And let's rerun the simulation. So we're going to run it. Of course, our axis is much higher. And notice again that we ran the simulation for 10 seconds. So when we run it, we're starting at 100 meters above the ground. It's coming all the way down, bouncing here at around 4.5 seconds. So notice that it took much longer to reach the floor. And of course that makes sense because we're dropping it from a higher altitude. And then it bounces up to, looks like around 50 meters. And it doesn't even reach the ground again within 10 seconds. Of course, again, that makes sense because we're dropping it from a higher altitude. So it's coming down, bouncing all the way up. So it's going to take longer to reach the ground. It's going to take longer to go up and then come back down. So if we change this time to, let's say, 100 seconds instead of 10 seconds, and we go back to the scope and let's re-simulate this. Now we can see sort of the same behavior. So it's coming all the way here, 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 here. Now let's change this back again to 10 seconds. And let's change this initial position to 10. So basically the way that we ran the first simulation, let's run this again. And one thing that you can do to scale the X and Y axis to something that's more meaningful for your simulation specifically is you can click this button over here and Simulink automatically adjusts the zoom so that your simulation looks better. So again, we're starting at 10 meters above the ground, it's bouncing back up. Now what I want to do is, instead of doing that, let's change the initial velocity. So again, we said originally that we were simply just dropping the ball. Now let's say what happens if you kind of throw it up before it falls down. So instead of just dropping it, you kind of give it a little bit of force to go up a little bit and then come back down. So let's say that the initial velocity is 5 meters per second in the positive direction. What happens now? So let's go ahead and simulate this again. And now you can see that essentially we're starting again at 10 meters above the ground, but because we're applying a force up so that it initially goes up a little bit, it goes above 10 meters to about, looks like 11 meters. Then it comes down, bounces back up, and we have the same behavior after that. And again, this makes sense because now we're saying that we're kind of applying a force up to make it go up a little bit above 10 meters and then come back down. Now let's do the same thing for a negative value over here. Let's say -5 instead. So now we're saying we're applying a force down when we're throwing the ball. Now you can see that we have a sharper decline over here than we did when we had a 0 meters per second initial velocity. And again, that makes sense because we're saying that we're applying a force down. So I want to do one more thing, and that's change this back to 0. Now let's say that we have, let's actually run this again first. So we see that when the ball bounces back, it bounces to around 5 meters over here. So this second bounce is around 5 meters. What happens if we change this restitution? And again, this is a representation of how elastic or how bouncy the ball is. So if we change that to 0.9, let's say, and let's go back to our scope, let's run this again. And now we can see that instead of bouncing back to around 5 meters, as we saw before, now it's bouncing back to around 8 meters on the first bounce. And again, that makes sense because this constant, what that represents is how bouncy, so to speak, the ball is, how elastic it is. In other words, how good it bounces back. And let's say that we had something like 0.2, for example. So those something that doesn't bounce too well, maybe like a baseball or something that's more heavy and less elastic. We would expect, of course, to see the bounce decay more quickly. And of course, we see that over here. We see that we have 10, then it bounces just a little bit and then it goes to 0. So let's change this back to 0.7. And I want to show you one last thing before we end, and that's that I talked about Payson simulations before, and I mentioned that sometimes that's helpful if you're trying to see stuff as it would happen in real life. So what I can do here is, again, when you say 10 seconds here, what Simulink is doing is it's running the simulation as if this were happening 10 seconds in real life. So it's giving you results for 10 seconds in real life. Now, it doesn't mean that your computer is going to take 10 seconds to do the simulation, because of course, this is a somewhat simple model for a computer to compute. Now, what you can do is you can change the simulation pacing and enable simulation pacing. And basically what that does is now your computer is going to take 10 seconds to run the simulation if you tell it that you want to simulate 10 seconds. In other words, I'm saying simulation time per wall clock second is 1. What that means is that for every 1 second that Simulink is giving you results for, your computer is going to take 1 second to run the simulation. And again, that's helpful because now you're going to be able to see the bouncing as if it were happening in real life. So let's see what that looks like. So again, I paste the simulation down, and now I'm going to rerun this simulation and watch what happens. So now this is looking as if it were bouncing in real life. We can see the bounce, every bounce, and then it settles down around 0. And let's just do it one more time. And again, this now, it becomes apparent why that simulation pacing sometimes is helpful or useful, because now you can see, okay, if I were to drop a ball in real life, this is how long it would take to bounce. So 2 seconds, 3.5 seconds, 4.5 seconds, 6 seconds, 7, 8, 9. And of course, you were able to see this before, but now you can actually see it in real time. So that's what simulation pacing is for. Sometimes it's kind of useful to just see that during the simulation, but you don't generally have to use it if you don't want to. Again, notice here that when I run the simulation, once I have disabled simulation pacing and I hit run, you can even see the simulation run, and it just gives you the whole result right away. All right, so I think this is a very thorough explanation of how to simulate a bouncing ball. I'm going to make this model available for download with the lecture resources. So if you're interested, you can download this model, play with it, play with some of the values, and you can use it for your own simulations as well as a starting point if you want to. And I'm going to rename this the bouncing_ball_model. And again, it's going to be available for